We're very happy for this week's Western Hemisphere Virtual Symplectic Seminar to have Yuan Yao speaking on Morse-Bott embedded contact homology and cascades. Take it away.
Hello. Let me share screen. I'm very happy to be here. Been a big fan of this seminar series. So let me start. Can you see my screen? Okay, enter full screen. Okay, so today I'm going to talk to you about Morse-Bott embedded contact homology and how to compute it in using the kind of the framework of Cascades. So the general structure of the talk, I'll start giving you an overview of embedded contact homology, then some kind of review how one version of Morse-Bott theory works in the holomorphic curve setting. Then I'll say, well, how to actually do it for ECH. And in the end, I'll say something about gluing, which is kind of the analytic engine that makes this all work. So introduction to ECH. So the shortest way to say this is ECH is a floor theory for contact 3 manifolds with generators, Rabe orbits, and differential counting holomorphic currents. And let me give you the basic setup. So you have a contact 3 manifold with a contact form lambda. Associated to this lambda, there's this Rabe vector field that's uniquely determined by this equation, these two equations. And to define ECH, you require lambda to be non-degenerate. So this is a technical condition that for each periodic orbit of the Rabe vector field, the linearized return map does not have 1 as an eigenvalue. For us, this will imply that all the periodic Rabe orbits are isolated and they're far away from each other. And so, as I said, this is a theory that counts J holomorphic currents. So where do they live? So they live in a symplectization of y, which is you cross y with r, and you equip with this symplectic form, which is the one that's commonly used in lots of other settings. And you choose a generic, almost complex structure on the symplectization, compatible with lambda in the following sense. J is invariant in the symplectization, the r direction. The contact structure is the kernel of the contact 1 form, and J preserves that, and it sends the vector field pointing in the symplectization direction to the Rabe vector field. And this is also the standard thing you would put, conditions you would put in almost complex structure symplectizations. So what are the generators? I'm going to give you the chain complex generators over Z2 coefficients. They're given by orbit sets, which is kind of different from other floor theories. So an orbit set is a collection of Rabe orbits, alpha I, and each alpha I has to be embedded. And together with that information, is information of a positive integer, which is called the multiplicity of alpha I. So the way embedded contact homology talks about multiple covers of Rabe orbits is to say, well, I have an embedded Rabe orbit of higher multiplicity. Okay, and yeah, okay. And the differential is given by a count of J holomorphic currents in the symplectization. And what is a J holomorphic current? A J holomorphic current is given by Ci and Ni, where each Ci is a somewhere injective J holomorphic curve, and Ni, again, is its multiplicity. So the way ECH talks about multiple covers of holomorphic curves is to say, here I have some somewhere injective curve with higher multiplicity. Okay, so now I've told you like the orbit sets and J holomorphic currents, though, how do they talk to each other? And they talk to each other via the following. So if you have an orbit set, we say a J holomorphic current, C, script C, is positively asymptotic to alpha at s equals plus infinity if it converges to alpha as a current. So how do I say this more precisely? So you take the symplectization, take a slice of the symplectization so fix S cross Y3, which is a copy of the contact 3 manifold, and you intersect it with a J holomorphic current. Then this is generically, this is a one-dimensional manifold with multiplicity. Then you say this one-dimensional manifold with multiplicity converges to alpha, which is again a collection of one manifolds with multiplicity as a current. To say this in a slightly more technical way, this is the kind of the standard way you talk about convergence as currents. So for for any one form on a contact 3 manifold, the integral of this one form over the kind of the holomorphic curves restricted to this slice of the symplectization, weighted with multiplicities, converges to the integral of this one form over the Rabe orbits with multiplicities. Are there questions about this? So I'll give you an example to tell you what I'm talking about. So, and again, a similar condition holds like if C is negatively asymptotic to alpha at S equals minus infinity. And let me just say, like, this is the only way we're going to talk about convergence of currents to periodic orbits. And this is kind of different from how other floor theories do it. So let me give you an example. So suppose C is somewhere injective J holomorphic curve that has two positive ends, each asymptotic to the sorry, I have an edit button. Do I have an edit button? Okay, let me not worry about it. Okay, so you have a J holomorphic curve that has two positive ends, each positively asymptotic to a simply covered Rabe orbit gamma, which I show here. Then we have C1, the current C1 is positively asymptotic to gamma 2, because if you look at the plus infinity side, it's kind of asymptotic to it with multiplicity 2. And if you look at C2, then it's positively asymptotic to gamma 4, because if you increase the multiplicity of your curve. And this, in some sense, this is part of the difficulty of the theory, is because when you say a J holomorphic curve is positively asymptotic to gamma 2, it could do so in many ways. Here I've shown you two ends that simply cover gamma once each. And another way is to have an end that a single end of C that doubly covers gamma. And from the current perspective, they're the same. Okay, are there questions? Okay, so let's keep going. So now I've told you how to count J holomorphic, how to, like, what are the generators are and what the J holomorphic currents are. We need to pick out some special collection of currents in order to count them. And we do so with the help of an ECH index. So suppose you have a J holomorphic current, which is some curve with multiplicities. We can assign to it an ECH index given by I of C is equal to Q tau C, C tau C, mu tau of C. I'll briefly tell you what these terms are. So tau here is a choice of trivialization of the contact distribution over each Rabe orbit. And Q tau is, once you've chosen such a trivialization, is some kind of relative intersection number with respect to tau, using the fact your curves are kind of two-dimensional. And C tau is a relative first Chern class, also with respect to tau. And mu tau is some specific combination of Conley-Zinder indices that you have in ECH. And each of these terms depends on the choice of trivialization tau, but combined, they do not. And the ECH index only depends on the relative homology class of the current. Okay, and the key input that makes ECH work and the reason you define this index is the following. Suppose you have a somewhere injective holomorphic curve, then there's an index inequality that basically says the ECH index is an upper bound for the Fredholm index of C, which is the dimension of the moduli space the curve C lives in. It's even slightly better than that. It's IC minus 2 delta C. So delta C is some count of singularities of C, which is always non-negative. So just by looking at this inequality, you realize if you count restricted curves with ECH index 1, if they are to exist at all, they must be rigid. Their Fredholm index must be 1, the 1 coming from the kind of translation direction. And it has to be embedded. It cannot have any singularities. And let me just say, like, the proof of this index inequality involves just intersection theory in 4 dimensions. Specifically, you need to understand the right of a J-holomorphic curve. Let me just say what this is. Let's see. Give me 1 second if I figure out I can try to like write on my screen. Let me give me 1 second. So sure. Okay, not working.
I'm not sure if annotation is turned on for the Zoom
if
room.
someone, okay, then I'll do without it. If someone with Zoom powers can turn it on, that would also be helpful. Okay, so let me then just describe this in words. Where does the rise of a J-holomorphic curve come from? So if you take us for very large values of the symplectization direction, if you take the intersection of the J-holomorphic curve C with a slice of the symplectization, namely a copy of the contact manifold, here as it's very large and positive, this intersection is like a one-dimensional manifold in your contact manifold. And because at positive ends it converges to rape orbits, this set is actually a braid around each rape orbit that kind of converges to the rape orbits. And the proof of this kind of intersection inequality kind of involves like understanding the right of this braid. And that's kind of what goes into this index inequality. Okay. So as a consequence of that index inequality, you can actually use the ECH index to pick out certain J-holomorphic currents with I equals 1. And it's a theorem originally first due to Michael Hutchings that if you have a ECH current, a current of ECH index 1, then the current must only consist of a single rigid non-trivial embedded J-holomorphic curve of multiplicity 1 and Fredholm index 1. And all the other components of the current must be trivial cylinders of different multiplicities. So this non-trivial components is what the differential is counting. And that's picked out by the ECH index 1 condition. So then you're in business, you can define the ECH differential by counting J-holomorphic currents. So if you have 2 orbit sets, alpha and beta, you can say the differential between them is some Z2 count of J-holomorphic currents of ECH index 1, positively asymptotic to alpha and negatively asymptotic to beta. So again, let me just say, like, unlike many other floor theories on the market, kind of like I equals C automatically tells you your curves are embedded and there are no multiple covers. And for the purposes of defining the differential, there's no transversality issues. Okay, so with some work, you can show this differential is well-defined because it's a usual compactness argument to show that such counts are finite. And it takes a lot of work to show d squared to 0 because let me just briefly say, because you impose convergence as currents. And for a given orbit set, there's lots of ways for a J-holomorphic curve to converge to this orbit set as a current. As I said earlier, you can have 2 ends converging to an orbit set, or you can have 1 end converge to an same orbit set. So these don't always match. So you have to glue some branch cover trivial cylinders to make the gluing work. And that's where a lot of work goes in. But with that, you have a homology theory, and you can show, again, very difficultly, that this only depends on the contact structure. And to show this independence usually requires passing to gauge theory, the monopole the from version of monopole floor homology. And let me just say, the reason we've been talking about currents and instead of just J-holomorphic curves is precisely because like ECH is related to this gauge theoretic invariant. But once you have this, you're essentially in business because you can import a lot of results from gauge theory to symplectic geometry via ECH, and this gives you a lot of applications to symplectic embeddings and dynamics of rate vector fields, et cetera, et cetera. Okay, that's my introduction to ECH. Are there any questions?
Could you remind us the definition of the items in this equality, like the gamma and the math frag S?
Okay, so I haven't told you what gamma is. Good catch, but the gamma is kind of some further grading information on ECH. This is basically the homology class of your orbit sets you're allowing. Y3 is your contact manifold, C is your contact structure. And this thing, I think, is a spin C structure, but I'm not so familiar with I don't quite remember the gauge theory set, but the point is here, look, some gauge theory. Okay, all right, let me move on. Sorry. So hopefully I've convinced you that it's a good idea to compute the ECH chain complex. But in life, sometimes we're confronted with contact forms that are degenerate with Morse-Bott degeneracies. Remember, when we defined ECH, we said the contact form has to be non-degenerate and the Rabe orbits have to be isolated. And I'm saying sometimes this is not the case. And one simple example is the contact T3. So with this following contact form and with this following Rabe vector field. And so if you kind of write it all out, the Rabe vector field appear in the S1 family. So instead of being isolated, there's like a circle's worth of Rabe vector fields. And there are more spots, which is kind of a technical condition. But the point is that instead of seeing isolated Rabe vector fields, you see a tori that are foliated by an S1 family of Rabe vector fields. And we'll call these S1 families Morse-Bott tori because for obvious reasons. And for us, we'll only consider the case where all Rabe orbits appear in Morse-Bott tori. In 3 dimensions, how the Morse-Bott families can't be too interesting, and this is one of the main cases. Okay, so all right. So suppose you have I have given you a Morse-Bott contact form. How can I define ECH anyway? So you can always perturb it to be a non-degenerate contact form. So we can define this ECH chain complex because non-degeneracy is a generic condition. However, it's often desirable to be able to compute homology using only the J-Holenford curves in the Morse-Bott setting, only using these information, because oftentimes the J-Holenford curves in the Morse-Bott setting are better understood because there's a bit more symmetry. The question is then, like, if I only want to look at J-Holenford curves in the Morse-Bott setting, what kind of objects should we count to define this chain complex? So to make this idea a little bit more precise, let me first, given a Morse-Bott contact form, let's first describe its perturbation into a non-degenerate contact form. Okay, so as I said, the Rabe orbits come in torus S1 family, so they foliate a torus. So let's look at such a torus. So here I've put coordinates. So Z is the Rabe direction. So moving in the Z direction is like going along a Rabe orbit. And X is the S1 family direction. So moving to different values of X corresponds to moving to different Rabe orbits in this S1 family. And Y is the normal direction to this Morse-Bott torus. Okay. Observe this picture. And so how do I perturb it into a non-degenerate picture? So I choose a Morse function on S1. This S1 is the same S1 as like the S1 family of Rabe orbits. And it has 2 critical points. So let delta be very small. That's kind of controlling the size of the perturbation. Then near each Morse-Bott torus, we perturb the contact form to multiply by e to the delta f of x. So remember, X is the S1 family of Rabe orbits. So that. And for delta small enough, all Rabe orbits of action less than L are non-degenerate, and they correspond to the critical points of F. So here on the left, you have some Morse-Bott tori, and these 2 orbits corresponds to the critical points of F in this. And after you perturb, these are the only Rabe orbits that remain, up to a very large action anyway. And one of the critical points corresponds to an elliptic Rabe orbit, and the other corresponds to a hyperbolic Rabe orbit. Okay, so if you have a Morse-Bott contact form for delta small, you can compute the ECH chain complex with non-degenerate orbits by perturbing to over here. And you can compute the chain complex by counting J delta holomorphic currents asymptotic to non-degenerate wave orbits. I put a little delta here because after you perturb, you also have to perturb the almost complex structure to make it compatible with a new contact form. But the question, of course, is then over here, after I perturb, I know how to count these curves to define my ECH chain complex. What do I count on the left-hand side? What do I do there? Okay, so to motivate this, I will tell you a little bit about the theory of cascades, which was introduced in Bourgeois' O2 thesis and Frauenfelder's O4 thesis. So consider lambda delta, which is after the perturbation with non-degenerate orbits, and a J delta holomorphic curve C delta asymptotic to wave orbits of lambda delta. So to find out what happens on the left-hand side, what I do is I take the limit delta goes to 0 and consider what kind of objects the objects C delta degenerate into. And this is a theorem that original version appeared in Bourgeois' O2 thesis. So if you take a sequence of delta n goes to 0, and you have a sequence of J delta n holomorphic curves with bounded energy and genus asymptotic to wave orbits of lambda delta n, then the subsequence converges to a J holomorphic cascade. So I haven't told you what a cascade is. I'll show you a picture on the next slide. But the one sentence way to say it, what it is it's basically an SFT building where the ends of the holomorphic curves end on Morse-Bott tori, and between adjacent levels, instead of the ends matching exactly, they match up to a gradient flow of the function f. So let me show you a picture of what a cascade looks like. So the red line is the S1 family of wave orbits. So each point on the red line is like a periodic wave orbit, and the horizontal line means it comes in the S1 family. U and V are J holomorphic curves, and U and V live on different levels. So they live on different SFT levels, and in between them, there's kind of the data of a single number t greater than 0. So what you do is, like, if you start at an end at V, and if you follow the gradient flow of f for time t in the middle level, you'll arrive at a negative end of u. And same for this end. If you start at the other end of V, you follow in the middle, you follow gradient flow for time t, you'll arrive at a negative end of u. And on the top and bottom levels, so the little diamonds corresponds to the critical points of f. And at the top and bottom levels, the top end of u and the bottom end of v, you follow kind of a semi-infinite flow of f to be connected to a critical point of f. So this is what kind of a two-level cascade looks like. Are there questions about this picture?
Question. So when you connect gradient flows to your from like the end of a curve, do you need to pick a marker?
Yes.
Okay.
Yeah. Okay. And so this is a two-level cascade. In general, this is just a general cascade is just this picture, but with more levels. And between adjacent levels, there's a data of a number that tells you how long to flow. So let me give you the definition. So a cascade is a sequence of J holomorphic max, U1 up to UN, and we think of UI as living in a level above UI plus 1. And between adjacent levels, there's a data of a single number. Could be 0, could be infinity, so that the ends of UI and UI plus 1 match up to a gradient flow of length Ti along each of these Morse-Bott tori. And the positive punctures of U1 and the negative punctures of UN are connected to critical points of F via the gradient flow of F. So that's basically this picture, but with more levels. Okay, are there questions about that? So let me give you some intuition about how this degenerate into cascade happens. So on the left, so from left to right, delta is going to 0. So here you have some homomorphic curve with some finite delta. And as you go to the right, delta is going to 0. And I've shown you where the symplectization direction is pointing. Sorry, I can only highlight the entire picture. So the diamonds here correspond to Rabe orbits that corresponds to the critical points of F, so non-degenerate Rabe orbits. And you have this holomorphic curve that's kind of on the right, kind of going down like that. And so the dotted circle lines corresponds to where the Morse-Bott tori are at. After you perturb, they're no longer Morse-Bott tori, but they're kind of still, that's where they were. Where they would have been before the perturbation. So what happens is that you have some J-holomorphic curve, and as it approaches these red Morse-Bott tori that you perturbed away, it will get captured, and it form this kind of long, low energy neck, which I've shown in green. And during this neck, it will tend to follow the gradient flow of delta times F. So in the green level, it's kind of going from one place to the other, follow the gradient flow of delta, which is the size of the parameter, times F, which is a perturbing Morse function. And as delta goes to 0, the size of the perturbing, so the gradient flow of delta F becomes very slow. That's why these necks become very long, because you need to flow for extra long time in order to get from the same place to another place. And as delta goes to 0, the gradient flow of delta times F becomes infinitely slow. And these become kind of like infinitely long necks, but they're not like infinite trivial cylinders, because overall they still from one Rabe orbit to a different Rabe orbit. And that's what these on the very right here, what these gradient flow lines have indicated are. So the J-holomorphic curve degenerates into some levels on the J-holomorphic curves and these infinite gradient trajectories in the middle, which I keep track of using an arrow. Are there questions about this picture? Okay.
Just one question. So in the theorem you stated where a sequence of curves converges to a current. So this is like not a compactified moduli space of currents, right? Like we're not allowing the usual SFT buildings or infinitely long trajectories or anything like that.
Sorry. So this is nothing to do. This is not currents. This is just an honest like SFT compactness theorem as you degenerate the non-degenerate contact form to a degenerate one.
Right. So like in a more general situation, I would expect, for example, that you need like infinitely long, like trajectories with.
Yeah. So in the
like
middle level
points.
here, I put t greater than 0, right, to the very right. In general, t could be infinite between adjacent levels.
I see.
Is that what you're saying?
T is allowed to be infinite between the.
Yeah. But they don't typically happen for index reasons.
Okay.
As long as you can have good control on index.
Mhm.
Yeah. Other questions? Okay. So this is how J-holomorphic curves degenerate into cascades. And then, then you can say, well, maybe in the Morse-Bott setting, I should count cascades. So the ECH index 1 condition I talked to you about earlier is a purely topological condition. So after degeneration to cascades, you can still make sense of ECH index 1. So the dream proof would be, well, here for delta greater than 0, you have some J-holomorphic curves. And as you degenerate and go to delta equals 0, here they degenerate in a one-to-one manner into cascades. And to define the ECH chain complex, you just count these cascades of ECH index 1. That's the dream scenario. Okay, so there are some difficulties with this picture, as is often the case. So, when a priori, when a sequence of J-holomorphic curves degenerate into a cascade, this is kind of like some kind of SFT type degeneration. And the resulting cascade could definitely have multiply covered components, and that destroys any hope of transversality in the classical setting, at least. Furthermore, so as I said, between let's say we get rid of that. So even if all the curves in a cascade are somewhere injective, there's still issues. because in a cascade between levels, there's kind of a single number telling you how long to flow. And to say this kind of a bit more properly is to say that the cascade kind of lives in the fiber product. And even if all your holomorphic curves are transverse, it could be the case its fiber product is not transverse. And then the moduli space of cascades is then difficult to work with. Let's say you have that. Even after that, so even if suppose all the cascades are transversely cut out, so you still need to prove that there's kind of a one-to-one correspondence between the cascades and the holomorphic curves after you perturb into the non-degenerate setting. So let me try to address these issues one by one. So the first two bullet points is basically saying the moduli space of cascades is not well behaved, that you don't necessarily have enough transversality. And the final bullet point saying you need some kind of correspondence between moduli space of cascades to the moduli space of J-homomorphic curves. So they're addressed by, at least in some cases, by the following theorems. So if you have a contact 3 manifold and you have a Morse-Bott contact form, after you've chosen some generic choice of J, the space of cascades with ECH index 1 and genus 0 is a well-behaved moduli space. It's discrete, finite, and transversely cut out. So this is in part using the ECH magic to say, well, no branch covers can appear, and some intersection theory goes into this.
I have a question.
Yeah.
What does it mean for a cascade to have ECH index 1? Just the holomorphic curve components sum up to have?
Yeah, well,
their
so
ECH index sum up
you
to 1,
imagine.
or-
So let me give you give you the picture of a cascade. So if you imagine like using these green arrows are kind of gradient flow lines, right? You imagine like gluing in a cylinder for each of these arrows, and then you have kind of a relative homology class, and you can
okay.
define
So you consider the relative homology classes of the gradient flow parts as well.
Yes, but they're all 0. The Chern class and self-intersection are all 0 for these gradient flows. The interesting part comes from Maslov indices, but yeah, you can do this. Is something that can be done. Okay, so there's the difficulties, and there's one theorem that says, well, in the genus 0 case, the ECH index 1 cascades are nice. They kind of live in a nice moduli space. Then there's this theorem about how to glue cascades into J-homomorphic curves. So originally, some version of this appeared in Bourgeois' O2 unpublished thesis, not too many details. And then there was Bourgeois' Oancha's gluing theorem for cascades for symplectic homology. And the version I'm stating below is in this year's preprint, and it kind of uses very different gluing techniques, and it's kind of like 100 pages of gluing. So if you have like a J-homomorphic cascade, I don't have to worry about genus, I don't have to worry about ECH index, but as long as it's transverse and rigid, then after a small perturbation of delta, a small enough perturbation delta, it can be glued uniquely to a J delta holomorphic curve up to translation in the symplectization direction. And combined with the previous theorem, and there's at least now some cases where we can use cascades to compute ECH. So let's suppose you have a contact manifold with a Morse-Bott contact form. If after the perturbation, into a non-degenerate case, if all ECH index 1 curves have genus 0, then if you can show this, if after you perturb all the ECH index 1 curves have genus 0, then you can compute in the embedded contact homology in the Morse-Bott setting by counting ECH index 1 genus 0 cascades. So that's basically the previous two theorems to get put together. And you can ask, does this ever happen? And well, yes. So this theorem applies to T3 and Eli Lebeau's thesis, T2 bundles over S1. It also applies to boundaries of concave and convex toric domains, which we describe a little bit below. So consider the moment map from C2 to R2 given by the usual torus action. If you don't know what that is, just look at this map. So if you have a smooth function from 0 to A, from 0 to B is a smooth function mapping 0 to B and A to 0. Don't worry, I'll draw a picture of this function. But you should remember gamma f is the graph of f, and delta of f I used to denote the region bounded between the graph and the xy axes. So your function looks like this. And the red is the graph of the function, and the purple is kind of the delta f. And up to some technicalities, which I won't describe in too much detail, but if delta f is convex, then the pre-image of delta f under this moment map is called a convex toric domain. And if delta f is concave, then the pre-image of delta f under the moment map is a concave toric domain. In any case, the pre-image under the moment map of the graph of f is a contact 3 manifold with a Morse-Bott contact form. And the periodic rape orbits are basically are described as follows. There are two non-degenerate elliptic rape orbits corresponding to the intersection of the graph with the xy axes. And then for each x in 0a in the x-axis, so that the derivative of f is rational, the pre-image of this x is a Morse-Bott torus of rape orbits. So it's very Morse. There's lots of Morse-Bott tori in this contact manifold. And with some topology calculation, you can show, well, if you perturb away all the Morse-Bott degeneracies, then all ECH index 1 curves have genus 0. Hence, the previous corollary applies. So you, at least in the case of concave and convex toric domains, you can compute the ECH chain complex using some count of cascades. So there's some content to the theorem I described. Okay. So gluing. So before I go on to gluing, are there any questions?
Yeah. So do you think you could use this to compute, say, periodic flow homology of like integrable surface maps? I feel like that would be
the PFH is
think
kind
about
of
that.
analytically, there's not much difference from ECH to PFH. So the ECH index will continue to make sense, and the theorems that I told you will continue to make sense, and the difficulties with transversality of the fiber product will continue to persist. So if you can find situations, so let me just say, like, so here I said you can do it when it's genus 0, and but you can, there's actually, this condition can be more relaxed. There's like this, in this preparation, I tell you exactly how much transversality you need to be able to run this machine. And you can maybe even work it out for genus 1 case. But yeah, there's more wiggle room in this proposition. I just stated this cleanest one I can think of.
Yeah. Also, what role does the genus play again?
Oh,
Well,
so
maybe you were about
basically,
to say that, but
yeah. So
Yeah.
so here, like I've outlined 3 difficulties. Like the main difficulties are the first 2, like the space of moduli space of cascades is may not be well behaved, even after you impose the ECH index. So it turns out the first one isn't so much of a difficulty. The main issue is the second one. So the cascade has to be kind of like a fiber product. And the ECH index doesn't tell you very much about the transversality of this fiber product. So if you're in genus 0, the fiber product, like, it's very easy to make that fiber product transverse because you have that flow line. The length of flow is kind of an input, and it's kind of something that helps make the fact you have a flow line you can change is something that can help you make your fiber product transverse. But in more complicated situations, when you have genus, there's lots of evaluation maps. And I'm not saying you can't do it. I'm saying the usual proof that how do you show fiber products are transverse? Well, you usually pass through the universal moduli space and you wiggle J and make evaluation maps transverse. I'm saying that proof doesn't work if your cascade is very complicated and have lots of genus. But there could be other ways if you're more clever and you can get around it. I think genus 1 you can get around it. But yeah, and after you have that, the first bullet point is resolved by thinking about the ECH index.
That's very interesting. Thanks.
Okay. Yeah. Thank you. Okay.
So sorry, just to follow up on that. So
Yeah.
could it be the case that actually in general for all genus that these index 1 cascades are regular, or do you know an example where even for generic.
Could be. I don't know how to prove it. So I can think of an example in the universal moduli space where the thing is not transverse. The reason but this doesn't say anything because you can maybe set up a more clever choice of universal moduli space and get around it. And the reason behind this is very simple, because when you have cascades, the J on different levels are the same. So if you have a cascade with lots of levels in the universal moduli space, the same curve could appear on different levels. And when that happens, the ends of the curve cannot be perturbed independently of each other. And that's causing you difficulties with transversality. So this is what goes wrong in the most kind of naive implementation of this transversality argument. There may be ways to get around it. For genus 1, I think maybe. I haven't thought about more complicated situations.
I see. And what role does the metric play here? Is the statement that you fix a Morse-Mill metric or something, and then you get transversality for generic J, or is it?
You don't have to worry about the metric. It's a completely a statement about J homomorphic curves.
I see. So it's arbitrary metric and generic J.
Yeah. Okay, so let me go on to gluing, which hopefully won't be too painful. So let me remind you of the key objective. So given a transversely cut out and rigid cascade, these are very natural definitions. I won't tell you what they are, but they're just very natural definitions. After you do a small perturbation of the contact form of size delta, you want to glue it to a J delta holomorphic curve. And we use the gluing setup from Hutchings and Taubes, their obstruction bundle gluing paper setup. You don't actually need to do any hard obstruction bundle gluing, but their setup allows kind of more flexibility. And the general strategy is kind of the gradient trajectories in a cascade kind of behave very differently from a J holomorphic curve because these things are very slow. So the strategy is to separate the dynamics over the gradient trajectory segments from the dynamics of the J holomorphic curves in the cascade. And precisely how am I going to do that? The strategy, which I won't explain in full, but I'll at least sketch, is that we write down the PDE for each gradient segment, and we write down the PDE for each J homomorphic curve in the cascade. And finding a gluing is equivalent to solving a system of coupled PDEs. Okay, so let me describe the main difficulty with gluing before I start to tell you about the construction. There's kind of two difficulties. One is, look at this cascade. So in the intermediate level where I've drawn this T, so there's less transversality than you would usually expect. Usually when you try to do some kind of Morse-Bott gluing, the two evaluations have to be maps onto this intermediate level have to be transverse on the nose. But here in the cascade is saying the evaluation maps have to be transverse up to this extra gradient flow time. So there's less transversality than you would have in a naive gluing problem. And that's okay. Then you try to get around it saying, well, let me wiggle things and see if I can still find a solution to this equation. And that's kind of the second difficulty, is that so the J homomorphic curves and the gradient flows kind of behave kind of very differently. The size of the vectors kind of don't mesh very well. So let me explain what this means. So imagine on the left-hand side, you have this cascade, and you try to pre-glue them for a gradient trajectory of length t. And this is a very long gradient trajectory. Its length is of size t over delta, because delta is going to 0. Now imagine you slightly perturb v to make its end land somewhere a little bit further away, and then you try to glue them together. Then you have to pre-glue them together a gradient trajectory of t prime over delta. And from the perspective of v, you move its ends only a little bit to be t prime. But after you divide by delta, this means that the length of the gradient trajectory you need to fit between them has increased by a very large amount, because the difference between the right and left picture, the difference in length of the gradient trajectory you need to fit between them is of the size t prime minus t over delta, and delta is going to 0. So from the perspective of, so in a cascade where you have kind of finite flow times in the middle, you know, you can, a small perturbation in the holomorphic curves could translate into a very large change in the gradient trajectories that connect between them, precisely because delta is going to 0. And that's kind of where all the difficulty is. You have to really keep track of and make sure your vectors are not too large. Okay, so this is the difficulty. I'll try to explain how to address it, some situations of this. So to explain to you how I think about gluing, the way Hutchings and Taubes do gluing is kind of very different from the implicit function theorem way of doing gluing. So just to illustrate their methods, I'm going to study a very simple toy problem. Suppose you have a non-degenerate wave orbits and you have two trivial cylinders, U and V. I'm going to attempt to glue these two trivial cylinders together, pretending I don't know how they should be glued together. I'm going to glue them by running Hutchings and Taubes machine to give you an illustration of how that machine works. So here in the picture below, I've drawn two trivial cylinders. And here's the symplectization direction. The two trivial cylinders are U and V. R is the gluing parameter. So at distance R, I cut them off. And here I've drawn two cutoff functions, beta U and beta V. And beta U is mostly supported in U. And then after the gluing parameter, I kind of make it decay slowly to 0. And beta V is mostly supported in V. And after a bit, I make it slowly decay to 0 after it leaves V. So with these gluing parameters, I can pre-glue U and V together. And then I can try to say, well, what kind of deformations I have to do to make the pre-gluing an honest gluing. So what are the set of deformations I'm allowed? So this is a simplified picture. There's more bells and whistles you have to add in general. But this is just naively, I have psi of U, which is like the vector fields that deform U living in the Sobolev space of U pullback of the tangent bundle of M. M is your symplectization. It's just the ambient manifold. And you have psi of V. And these are vector fields that can use to deform U and V. So what I'm going to do is that I'm going to deform the pre-glued curve with psi U cut off with beta U and psi of V cut off beta V, and ask, well, when is this deformed curve going to be J holomorphic? When is this equation going to have a solution for any choice of psi U and psi V? So this equation can be split up, so it can be written in the alternative form. So the point is I'm going to try to split it into two equations. So just this equation as is can be written as beta U theta U plus beta V theta V, where beta theta U and theta V are just different analytic expressions I give below. So you should think of theta U as an equation that's mostly taking place in the domain of U, and theta V is an equation that's happening over V. So what's theta U? It's basically the linearized Cauchy-Riemann operator applied to psi U plus some cross terms with psi V plus some nonlinear terms. And same thing with theta V. It's the linearized Cauchy-Riemann operator along V applied to psi V plus some cross terms plus some nonlinear terms. So theta U should be thought of as an equation over the cylinder U, and theta V should be thought of as an equation over V. So finding a solution to this J holomorphic curve.
I'm a little confused.
Yeah.
But isn't psi V a vector field over V star TM though, and it arises as a term in beta U?
No. So beta U is a cutoff function. Beta U is a cutoff function.
I mean theta U. It takes as input psi U and psi V. And
Yes.
psi V lives in V star TM.
Yes, but where it's cut off, that you'll only see because of this cutoff, you'll only see the parts of psi V where it's very close to U already.
Okay.
Is that okay?
Thanks.
Okay. So finding a solution to the J holomorphic curve equation, well, I can just solve this system of nonlinear PDEs, and then I have a gluing. So how am I going to solve this system of nonlinear PDEs? So, okay, let me go to that on the next slide. Please burn this slide into your memory. So how am I going to do that? I'm going to solve them one by one. So first, I'm going to fix psi of u to be small. I'm going to fix this. Then I'm going to solve theta v. So theta v, I should now think about an equation with independent variable psi of v, and psi of u is already fixed. And theta v is now an equation over the trivial cylinder v. Okay. And because it's a trivial cylinder, there's a right inverse qv to dv. Then solving this equation is equivalent to finding a fixed point of this map. And because psi of u is fixed, and this term, the f of v is kind of quadratic, this term, this map I've written down is a contraction mapping. So by the contraction mapping principle, it has a unique fixed point. So this fixed point depends on the psi of u, right? Because I fixed psi of u to view this as a contraction mapping principle. So the solution I get out of this contraction mapping principle is going to depend on psi of u. Does everyone follow thus far? Kind of. So now I've written by solving theta v, I've written psi of v as a function of psi of u. I'm now going to feed this back into theta u. So we plug this. So the theta v is telling us for any psi of u, I can find a psi of v that depends on u that solves this equation. Now I'm going to feed this equation into theta u, and I can show with just by taking some derivatives, I can show that kind of psi of v depends in a nice way on psi of u, because all the derivatives are well behaved. So which then you can, after you feed this into psi of u, you're solving for psi of u via this fixed point, via finding a fixed point of this map. And of course, psi of u is a function that depends on psi. Of course, in this equation, psi of v is a function that depends on psi of u, and your only independent variable is psi of u. But you can show that this is still a contraction mapping. So therefore, there still exists a solution psi of u, and therefore you have solved psi of u and psi of v, and therefore there's a gluing. Are there questions about this? So what did I do? There's kind of like, there's two equations, psi of u, theta v. I'm saying fix psi of u first, then I'm going to solve theta of v first. And theta of v can be solved by using contraction mapping principle. And the solution is psi of v in terms of psi of u. Okay. Now now I can write psi of v as a function of psi of u. And then I feed this psi of u into theta of u and solve theta of u with a contraction mapping principle. And both equations are solved, and we have a gluing. Does that kind of make sense? Are there questions?
I see. So psi of v, psi of u, this is not like a composition. It's when you solve that first equation,
Yeah.
Your solution for psi of v is dependent on psi of
Yes,
u.
it's dependent on psi of u. Yeah. And
Okay.
then you can show this is a nice dependence. So you can feed this back into psi of u, which then you solve with another contraction principle, precisely because this is a nice dependence and this is still a contraction mapping.
Okay, thanks.
Okay. So this is how to glue two trivial cylinders together if you didn't know how to do that beforehand. So now let me give you a slightly more involved case that kind of shows up in Cascades. I should mention, this is also, if I had a pen, I would write this down, but this is also written in the appendix of this ECH and Open Books paper jointly with Ko Honda, Vincent Collin, and Paolo Gigini. I apologize if I butchered your names, but yeah. Okay. So this particular gluing. Sorry. Oh, thank you. This gluing scenario. The gluing for this setup is kind of done in that appendix. So let me explain how to glue a semi-infinite trajectory. So let's say you have a J-holomorphic curve U that has ends on a Morse-Bott torus, and it's connected to a critical point of F via a semi-infinite gradient trajectory. So now I want to glue this to a J-holomorphic curve. This is kind of how to glue one level cascades. There's only one level and it's connected by a gradient flow. So how do I glue it? And let's, for simplicity, let's say it only has one positive end. So let's think about U. It has an end on the Morse-Bott torus. So what are its space of deformations? It has kind of two kinds of deformations, which with psi of U, which is the same kind of Sobolev vector fields along the entirety of U. There's another kind of deformation that's kind of moving the end along the Morse-Bott torus. So dx, I remember dx is a vector field that's kind of moving, that's responsible for moving to different, that's x is a direction that's like moving to different grape orbits in the S1 family. And there's kind of this asymptotically constant vector field that's responsible for moving one of the ends of U along the Morse-Bott torus. So here I've drawn U in blue and the effect of U plus P dx, this vector field in brown, I think. Are there questions with this picture? So if you deform with this vector field, you'll get this brown picture over the positive ends. So this is the space of deformations for U. Okay, so what am I going to do? So I'm going to try to run above previous strategy by doing the following. For each fixed pair, psi U and P, we pre-glue a different gradient trajectory to the curve. We pre-glue a gradient trajectory VP to the curve U plus P dx. So here in blue, you have just U, and then you pre-glue a gradient trajectory that kind of goes off to the critical points. But after you deform the vector U with P dx, you've moved the end along the gradient, along the Morse-Bott torus. So then you pre-glue it to a different gradient trajectory that starts and ends here. And I'll call this different gradient trajectory VP. So in some sense, I've made the pre-gluing depend on the asymptotic vector field P dx. So then you can run the same story, basically. You have psi P, which is a vector field over VP, and P that deforms that's responsible for deforming VP. And you can pre-glue the curve U plus P dx, pre-glue with VP, and you deform this curve using psi U and phi of P. Sorry, this is a typo. This is phi of P. And beta U and beta V are the same cutoff functions as before. And the result of the deformation is this map. And you can ask, well, when is this map give you a J holomorphic curve? Okay. So again, you split this equation into two. One is an equation over U and another equation over VP. So here it's basically the linearized, it's equivalent to solving this system of equations. Theta U is an equation living over U basically, and theta VP, which is an equation that lives over VP. And here I'm making this theta P dependent on P. I'm doing this on purpose. This is not a mistake. For each P, I get a different theta VP here. But the point is that still you can write this. This is some linear operator plus some cross term, some nonlinear term. Same here, some linear operator, some cross terms, and cross up some nonlinear terms. So what am I going to do? So for fixed psi U and P, the equation theta VP has a unique solution that depends on P and psi of U using the contraction mapping principle. So next, so this gives a solution to theta VP. We next vary V psi U and P as input to theta of U. Note as we're varying P, we're changing the pre-gluing. So here, as we're varying P, we're changing the we're kind of moving in a one parameter family of pre-gluing, but that's okay. After some parallel transport, you can identify all of these functions together with psi P. And then you look at the equation over, this is an equation over U now. Its independent variables are psi U and P, and it has cross terms that depends on P and psi of U. But this is you view this as purely as an equation over U, and you can show that this psi of P also depends nicely on the input variables P and psi of U, which you need to do after a kind of some parallel transports. But this can also, psi of U, theta of U can also be solved with the contraction mapping principle. And therefore, you have solved both of these equations, and hence you have some gluing. So I know I'm out of time. Can I just take people, of course, are free to leave, but can I just take 2 minutes to finish the rest of the slides? That's okay.
Yeah, that's okay.
Okay. So let me just briefly outline why. So that's how you do it for like one level cascades, but the story is kind of quite a bit harder for when you have finite flow gradient trajectories, because previously, as you will recall, as I varied P, this kind of the domain of VP didn't change. It's still kind of some semi-infinite gradient flow. But when you have finite trajectories, you have this picture here. When you move one of the ends of V, the gradient trajectory, you have to pre-glue between them. It's actually drastically lengthening and shrinking when you vary the pre-gluing over both sides. So of size like 1 over delta as delta goes to 0. So you still split it into 3 equations and try to solve them systematically, but you have to work much harder to see what's the middle equation. So given two, so the middle equation can always be solved, but you have to work much harder to understand how it's coupled to the rest of the equations over U and V. So to do this, let me not get into the technical details, but you have to like do another pre-gluing. So you have to like you do the pre-gluing, then you pre-glue another set of solutions on top of the original pre-gluing. So to actually try to understand as you move these ends around, like how the equations are coupled to each other. And that's where most of the difficulty is. And I can talk about this more towards the end, where I can also edit I can also annotate. But then, yeah, so for finite case, when you move these ends around in the pre-gluing, you have this drastic lengthening of the gradient flow between them. So, but you do a second pre-gluing to keep the errors under control. And once the gluing theorem is established, there's kind of a standard box of tools in Hutchings and Taub to show how to show the gluing is unique when you try to glue using this framework. And that's the correspondence theorem. And here are my references. Thank you.
Great, thank you. Let's give Yuan a round of applause. Are there any questions for the speaker?
Yeah, so do you expect to write down the UMAP in the same way by counting cascade, index 2 cascades with the point constraint?
So the issue is not the analysis. The issue is, again, with transversality. The moduli space of cascades of ECH index 2 might not be well behaved. Yeah, so if you can show that via some genericity argument, which I don't know how to do, or via some other means specific to your geometry, you can show the moduli space of index 2 cascades well behaved, the gluing will just go through. So the difficulty is with transversality, basically.
Yeah, it's good to know.
Yeah. Other questions?
So maybe just to clarify, the role of the cascades is to allow you to limit to degenerate orbits by, like, if they come in a family, then you can kind of slide from one to the other in your cascade.
The way I think of it is as follows. You give me a contact manifold and I want to compute its ECH. And sometimes your contact manifold is Morse-Bott, so your Rabe orbits come in families. And you want to ask, how do I still compute ECH when it's Morse-Bott? And of course, you can always perturb, but how can I compute ECH only using the information in the Morse-Bott setting, only using the Morse-Bott, by only considering holomorphic curves in the Morse-Bott geometry? And the way that I'm saying is that in order to do that, you count, instead of counting holomorphic curves, you count cascades of ECH index 1 in the Morse-Bott setting that look like this. And the theorem is that if you count cascades with ECH index 1, this will automatically compute for you the ECH chain complex after you perturb away. So this is a kind of a computational tool for how to compute things in Morse-Bott settings.
Yeah, I mean, if you had the UMAP, it would make computing ECH of an it would make computing the UMAP of ECH of an ellipsoid very easy or something, because then it's completely integrable, and the only index 2 cascades are with a point are just these gradient flow
Well, you
lines.
have to rule out
Yeah.
branch covers, right?
Oh, yeah, fair enough.
That's I mean, so if you can show if your cascade can only have one level for whatever reason, then you don't have branch
Yeah.
covers.
You can do this with intersection theory, I think.
Okay. Yeah, so so this work in preparation will come out soon. I'll tell you precisely how much transversality you need, and yeah, then you can see whether it works to the setting.
Can you say again what you have to think about when you're gluing these cascades? Like that's different than the non-cascade setting.
So right, so let me give you this picture. So if you look at the middle here, where I've drawn the line on which I've drawn a T, right? I can't edit, but okay, let me maybe this will help. So you have a cascade. Oh God, this is probably worse than before. So kind of like, so the cascade is saying these two ends have to match up to some gradient flow time T, right? So usually, like how you would imagine, usually without breaking the Morse-Bott symmetry, if you wanted to glue Morse-Bott SFT buildings together, you would say they meet on the nose here. And the two evaluation maps have to be transverse to each other, right? Then there's a kind of a standard theory that tells you this can be glued. This is all purely in the Morse-Bott setting. But as you go from Morse-Bott to non-degenerate, so there's kind of, it's not evaluation maps being transverse, it's saying evaluation maps transverse to evaluation. So some flow time, gradient flow composed with the evaluation map. So this notion of transversality is weaker than this one. So because it's, it's transversality up to this translation in this direction that you have. So this is kind of why, like the standard gluing, the usual, the way how you would glue things here doesn't quite work over here. There's not enough transversality, but you can still get around it. And that's, yeah.
Oh, I have one more question. If
Yeah.
it's not,
Please.
holding back, or wasting people's time. But I was wondering if you could indicate how this uniqueness part of the gluing argument will work.
Yeah. So
because from what I remember, at least for your toy example, you're solving theta u plus theta v is equal to 0.
Exactly. Yeah.
But then you actually show that they're individually 0.
Yeah. So it works something like this. This is kind of purely within Hutchinson taps. So, so you have U and V here, and you have imagine you have some solution. Let's try a different color. You have a solution over here, right? And the gluing is happening over here. This is the gluing parameter. Okay. And this solution automatically solves theta U and theta V away from the gluing region, right? So over here, the idea is kind of look at what this segment is. And okay. How do I say this? Okay, so it's not so hard to show the equations theta U and theta V has a unique solution. This system has a unique solution, right? And the next thing you want to do is that if you have a curve degenerating into this building, it has to come from a solution of this, right? So the way you go about this is you have some solution which I've drawn in red. So away from the gluing region, it also automatically solves theta U and theta V, right? So then you need to figure out, so let's call this solution like phi U and phi of V. then you need to figure out some way to extend this solution here, phi of u and phi of v, so that the extended solution is a solution for this system of equations, right? And there's a way to do it. This is basically by considering what happens in a trivial cylinder case, and it's basically saying there's kind of this restriction map from psi of u to like psi of u restricted to this S1, and then there's psi of v restricted to psi of S1, and basically you can say there's a unique solution over this finite trajectory satisfying these restriction conditions with these kind of that match psi of u and psi of v over these S1. And then there's some further like contraction mapping principle to find you a solution to extend these bits over in this intermediate region. It's a bit hard to explain, but the argument is not that hard. It's the basic idea is you already have a solution, you figure out how to extend them so they actually solve these two particular equations. Does that kind of help?
Yeah, that's pretty helpful. Thank you.
Okay.
I have a question.
Yeah.
If I continue, have you computed any particular example, the cascades for toric domains, or maybe the contact structure of the sphere? I mean, have you sit down and do the math?
So there's this this preprint by Con Choi, which is a former student of Michael Hutchings, that writes down the chain complex for many toric domains. I don't know if all of them, but that paper is kind of hard to read. It's 30 pages, but it has lots of adjectives. But in here you'll find many chain complexes for a toric domain, and they do use this cascade mod picture, but I don't know if I can say a bit more about it presently. But yeah, that's where you would go looking for them.
Okay, thanks.
Also, I would say like the computation for T3, which is done by Hutchings some time ago. It's basically also using there he completely computes the chain complex and using some very nice combinatorial model. And there they also use this cascade. I think he just assumed that's how the cascades work, and then he wrote down the chain complex. And I would just add one more thing is that the J homomorphic curves there are found by a previous paper of Taubes. Taubes wrote some of these very long papers. I forget their title, but you can easily look them up. It's like, here are all the holomorphic curves in this manifold. And
yeah, I think it's pseudo-homomorphic business.
Yeah, something like that. And then T3 is kind of adapting Taubes setup to T3 and using cascades to put them together into a chain complex. And then this is the parts I've read about this paper. I'm sure there's more in it, but yeah.
Thanks.
Okay, well, maybe if we have further questions, we can go into the discussion afterwards. Let's thank Yuan again. Thanks so much.